Hello everyone, I'm going to present joint work with Simeon Kublians and Alexandre Vigny on constant round distributed domination on graph classes with bounded expansion. We are studying the classical dominating set problem where we are given an undirected graph, so vertices connected by edges, and we are looking for a minimum dominating set or a dominating set of small size at least. This is a set of vertices so that every other vertex has a neighbor in the dominating set. So this vertex dominates these three vertices, and let's add this second vertex here. Now we have a dominating set. We are studying the local model of distributed computing where the network graph is given by the graph where we want to solve the domination problem. The vertices are equipped with unique IDs and they are allowed to send messages along the edges. The complexity of a distributed algorithm is the number of rounds required until every vertex tells if it wants to be in a dominating set or not. And our goal is to find a dominating set that is as small as possible. Now obviously there is a trade-off between the number of rounds that we invest and the approximation factor that we can get. If we are willing to invest a lot of rounds, we can just learn the whole graph. So in n rounds we can learn the whole graph. Then we assume that every node is equipped with a processor of infinite computational power. Using the IDs, we can then compute an optimal dominating set, and the vertices can agree on this dominating set based on the IDs. So we can compute an optimum dominating set. On the other hand, if we don't want to invest any time in communication at all, every vertex could just say, I want to be in the dominating set. Hence, without any communication, we could compute a dominating set, but this is obviously very bad. So it is known that in R rounds we can compute at most an omega of maximum degree to the 1 over r plus 1 over r approximation, which implies that we can compute a constant factor approximation. We need at least omega of log delta over log delta many rounds. We can compute a 1 plus epsilon approximation for any epsilon in polylog n over epsilon rounds. This combines very recent results of Ghaffari et al. And Rosen and Ghaffari. And the question we are asking is, what restricted classes of graphs can we consider so that we get constant factor approximations in a constant number of rounds? This question was first considered by Lenzen et al., who showed that in planar graphs we can get such a constant factor approximation in a constant number of rounds. These results were generalized more and more to bounded genus graphs, then very recently to classes with excluded topological minors by Chukrinov et al. And then in our work we show that it is sufficient that a measure called nabla1 is bounded. This is the edge density of bounded depth or depth 1 minors. I will explain in detail what this is in a second. We are building on the ideas of Chukrinov and on the ideas of Lenzen to achieve this result. And we can also show that this is the maximum where we can get with the current techniques. So if we want to push to degenerate classes, for example, this is one of the main open questions in this area, we would need completely different methods to approach this. So before I go into the distributed algorithm, let us revisit the classical greedy sequential domination algorithm. This works as follows. As long as the graph is not dominated, we select a vertex into a dominating set that dominates the most non-dominated vertices. So let's look at the following graph. We have a dominating set of size 2. We have 2 vertices dominating a lot, and then we have further vertices in the middle here. And I choose these vertices. They are also dominated by these. So our optimum dominating set is as follows. We have the two vertices here dominating everything, but the greedy algorithm proceeds differently. I have chosen the middle vertices as follows. I want that this vertex here dominates slightly more than half of the vertices. So these upper and lower vertices dominate everything. Each of them dominates half of the vertices. This one here dominates slightly more than half. So this is picked by the greedy algorithm. What remains are the vertices on the right to be dominated, and the second vertex is chosen so that it dominates slightly more than one half of the remaining vertices. So this vertex is chosen by the greedy algorithm, and this continues in this fashion. Yeah, always these vertices dominate slightly more than one half of what was dominated before. So how does the greedy algorithm perform? If G can be dominated with gamma vertices, with gamma I will always denote the domination number of the graph, so the number of vertices in a minimum dominating set, then I can dominate in every step at least a 1 over gamma fraction of the non-dominated vertices. Yeah, because I have a dominating set of size gamma, I have one of the vertices from the optimum dominating set as a candidate. In average, they must dominate a 1 over gamma fraction, so I know that one of the vertices must dominate 1 over gamma of the remaining non-dominated vertices. We can analyze this, and this yields that after log n, ln n steps, in fact, the graph is dominated, and in particular we compute an ln n approximation of a minimum dominating set. Now this is for general graphs, and we want to go to restricted graph classes now. And first we will tune this sequential greedy domination algorithm to classes that exclude some biclique. This is a complete bipartite graph. The KTT has t vertices on the sides, and then it is completely connected. So assuming that we exclude such a KTT, we can do better. We can tune the sequential algorithm. For example, planar graphs, they exclude a K33. Now assume we have our dominating set of size gamma, and let us assume that there is a vertex with very high degree. That means the neighborhood has size at least gamma to the t minus 1 times 2t minus 1. Then we can find a small set of size at most t minus 1 that intersects every such dominating set of size at most gamma. How do we do this? So let us assume here is our vertex with a very high degree. If this vertex is not in the dominating set, this means that there must be a second vertex that dominates at least a 1 over gamma fraction of this neighborhood of the vertex. If this neighborhood had size at least gamma to the t minus 1 times 2t minus 1, then this 1 over gamma fraction will have size still larger than gamma to the t minus 2 times 2t minus 1. If this vertex does not belong to the dominating set, I can continue the argument, then there must be a vertex dominating at least a 1 over gamma fraction, and so on. Yes. So what we are seeing, we are constructing here a complete graph on t vertices, because all the vertices share in their intersection of the neighborhoods the same vertices. If we intersect, we get vertices on the one side of the bipartition, and the vertices we are considering here on the other side are the other vertices of the bipartition. So this sequence of neighborhood intersections, this must stop after t minus 1 steps, otherwise we have constructed the complete bipartite graph KTT, which doesn't exist by assumption. So we can tune the algorithm as long as G is not dominated. We follow our sequence here of vertices of maximum degree and considering the neighborhood intersections. And instead of adding the one vertex of highest degree, we are adding those at most t minus 1 vertices now and add them to the dominating set. So instead of adding one vertex, we add at most t minus 1 vertices, but we are making extremely good progress here. We are not, as before, dominating a 1 over gamma fraction only, this is guaranteed, but we are also selecting at least one vertex from an optimum dominating set. So let us consider what is happening in the example that we considered in the beginning. Yeah, we had this situation here. And this vertex is the vertex of largest degree. So we are picking this. And then we are considering the neighborhood of this and see which vertex dominates the largest fraction of vertices. So let's say we pick this one here, we break ties arbitrary. So we are picking these two vertices instead of the one vertex, but we are making now major progress on domination. In the next round, less than half of the vertices remain to be dominated. Now this vertex in the second round here is the vertex that has the largest non-dominated neighbors. We pick it, we pick the one with the largest intersection, that is here, and then we are dominating in fact everything in the next step. Yeah, so this is a major improvement over KTT-free graphs. This works until the degrees become very small. Then we are left with a graph where we cannot apply this argument anymore, and then we perform as the greedy algorithm up to the factor t minus 1. So what we end up with is a log gamma approximation now. In our case we had a dominating set of size 2, and in fact we computed a 2 approximation here. So some observations in the sequential setting. We do not need to know gamma. Yeah, we say always if there is a vertex of high degree, then we can apply this, but we can carry out the algorithm without knowledge of gamma. We just take the vertex with largest degree, we take the next vertex with the largest neighborhood intersection, and so on. We also don't need to know t, so that KTT is not a subgraph of our graph. Yeah, we simply produce this chain, and we will get as a witness that there is a certain complete bipartite graph in our graph, but we simply do this algorithm and until it stabilizes, until we found a complete graph and we cannot get new intersections. So in parallel, in the sequential setting, this is a very easy to implement algorithm. Unfortunately, we cannot directly perform this in parallel. Yeah, if we assume that every vertex just determines do I have large degree or not, and then picks itself and the vertex with a large neighborhood intersection and so on, follows this sequence, this can lead to an unboundedly large selection of a dominating set. So the main part, or the great idea of Chukrinov et al. Was how to perform actually this greedy algorithm, this tuned greedy algorithm in parallel. We are not following exactly their lines of the proof, but we are rather first carrying out a pre-processing step that goes back to the work of Lenzen et al., which cleans up the graph a little bit. So the first lemma that generalizes this lemma of Lenzen et al. Is if we have a graph, then there are only few vertices with the property that their neighborhood cannot be dominated by a few other vertices. And this is now the point where this strange nabla 1 comes into play. Let me sketch the proof of this lemma and explain at the same time what the nabla 1 means. So assume we have our dominating set here of gamma many vertices, and then we have those other vertices who cannot have their neighborhoods dominated by a few vertices. So in particular, we need many vertices from the optimum dominating set that dominate the neighborhoods of these vertices. What we do now, we do a contraction of stars. Yeah, so for every vertex from the dominating set, we contract the neighborhood of this dominating vertex unless we have a conflict between two dominating sets, yeah, so that we break ties arbitrary. We don't contract into another vertex what has been contracted before. So this is a contraction of stars, and nabla 1 is exactly the edge density that you can get by such star contractions. Yes, so the edge density of star contractions is bounded. For example, in planar graphs, this is a special case of a minor. We know that the minors in planar graphs have edge density at most 3. Yes, so if we have an absolute bound for this nabla 1, like in planar graphs, then we can derive a bound on the number of vertices that cannot have their neighborhoods dominated so much. So why is this the case? Because we have a dominating set, every of the lower vertices here has at least 7 many neighbors in this contraction. The little tricky part, technical part, is that there can also be edges between those parts, and we have to pay attention that we don't overcount or that we cannot count them all the edges, but we must take care that if we sum the degrees, then we count several edges twice. Now we can locally test if the neighborhood of a vertex can be dominated by a few vertices. If this is not the case, then we can simply add the vertices to a dominating set. Observe that we need to know a bound on this nabla 1 coming with the input. Yeah, this is also the case for the work of Chigrinov et al. Because this nabla 1, or also the topological minor that is excluded, this is not a local property but a global one. So we need this as given with the input. For example, if we are working with planar graphs, we need the number 3 given with the input. Exactly. So let us call D1 the set of all vertices whose neighborhood cannot be dominated by few other vertices. We simply remove D1 from the graph and we mark all the neighbors as dominated. And by the lemma, this set is small, we are still within a constant factor of the optimum dominating set. And now let k equal to 2 nabla 1 of the graph. In the following, we can hence assume that all the neighborhoods can be dominated by k vertices by this pre-processing step. Now, in fact, the lemma shows something even stronger. If we fix a minimum dominating set D, these were the upper vertices in the proof of the lemma, then there are only few vertices with the property that the neighborhood cannot be dominated by few other vertices that come from D, yeah, not globally in the graph, but in fact from the unknown set D. Yeah? We cannot compute the set of D hat of vertices that have this property, but it will be very useful in the structural analysis of our dominating set algorithm that there is this hat, this set D hat of hidden vertices, of vertices whose neighborhood cannot be dominated by at most a constant number of vertices from the optimum dominating set. All other vertices, in fact, have their neighborhoods dominated only by a few vertices from D. And we call now D prime the union of D hat and D. And after this pre-processing step, we can now tune to a parallel execution of this tuned greedy domination algorithm. If we have now a vertex whose degree is larger than k to the t minus 1 times 2t minus 1, yeah? Earlier this was gamma, now this is k. A k that we can compute or assume that it's given with the input. If the neighborhood is larger than constant, this is super important, where the constant depends on nabla 1, then we can again do this argument, find such a sequence V1 to Vs of vertices, of at most t minus 1 vertices, that intersects our optimum dominating set. In fact, we will make it intersect with the set D prime. And furthermore, there is now a large technical part of the paper, which is also based on the very nice work of Chikrinov, that we can strongly limit our choice on the vertices in those domination sequences. Yeah, so if we are following this chain of vertices dominating smaller and smaller intersections, then these vertices that need to be considered here come from so-called pseudo-covers, and there are only very few pseudo-covers of the neighborhoods of the vertices. So what we do now, we pick the very last vertex of this chain into our dominating set. What is happening now? Very, very briefly. For all the vertices of large degree, we have our chains. We pick the last vertex into the dominating set. We do this in parallel. So what we get is for all the vertices a tree of candidates for this second vertex here. Yeah, there may be multiple vertices intersecting large parts of the neighborhood, but not so many because we restrict to pseudo-covers and we have this assumption on the density of nabla 1 of the star contractions. Again, we can use this argument. So we have a tree here of candidates that we can choose in each round, and this is bounded, the width of this tree. Furthermore, we know that the depth of the tree is bounded by our KTT argument. And finally, there comes into play this magical set D prime that we cannot compute, but that we use in our analysis. All the trees of all the vertices, they may be now interleaving, but they all, on every branch, contain a vertex of the set D prime. And this means, because we can analyze the choices or how the tree continues after encountering a vertex of D prime, that all the trees synchronize at the points of D prime, and then in total we show that we have a dominating set of bounded size. Yeah, so these are the three ingredients. This tree here is bounded in width because we have bounded density. It is bounded in depth because we exclude the KTT. And then there is the magical set D prime that intersects every such sequence, going over all the vertices in parallel, giving us in total a constant factor approximation of the dominating set so far. What we are finally left with is a graph with bounded degree. In particular, this must have a size linear in gamma. Yeah? In particular, the vertices of gamma that remain dominate only a bounded number of vertices. So the size of the remaining graph is linear in gamma. We can pick all the remaining non-dominated vertices and finish. What we then get as our final result is the result there exists a local algorithm that for any given graph G and an upper bound on the edge density of the graphs that you can get by star contractions. This computes a constant factor approximation in a constant number of rounds, where the constant factor depends here on this nabla 1 and the KTT that is excluded as a subgraph. Observe that if nabla 1 is bounded, yeah, so the edge density is bounded, then we also have a bound on T because KTT is a quite dense graph. So the key lemma goes back to the work of Lenzen. The other technical ingredients go to Chikrinov et al., but they are more general. In fact, they could potentially work all the way up to KTT free graphs, but the star contraction argument that we make in the beginning, we show that we cannot generalize this. So in particular, we can compute this constant factor approximation based on these techniques exactly on those classes where nabla 1 is bounded. Yes, the lemma does not extend to degenerate classes. We have an example for that in the paper. So the main question that remains here is What are the most general classes on which we can compute a constant factor approximation in a constant number of rounds? Thank you very much for your attention.